In the vast cosmos, there are real monsters, black holes. These are regions where gravity is so intense that nothing, not even light, can escape. Black holes push the laws of physics to their breaking point, challenging our understanding of space, time, and existence. Once just a wild idea from Einstein's theories, we now know black holes are real. We've seen their effects, even captured their shadow. They shape galaxies and force us to rethink the universe itself. Our quest to understand black holes is a journey into the unknown, blending cutting-edge technology with human curiosity. Let's begin our exploration of these cosmic enigmas. To grasp black holes, we must first understand gravity. Newton saw gravity as an invisible force pulling objects together, explaining everything from falling apples to planetary orbits. But Einstein revolutionized this view, proposing that gravity is the warping of space-time itself by mass and energy. Imagine space and time as a flexible sheet. Massive objects create dips, and smaller objects follow these curves. The sun doesn't pull the Earth, it bends space-time, and the Earth moves along that curve. This new vision explained not just orbits, but also predicted that gravity could bend light and slow time. Most dramatically, Einstein's theory showed that if enough mass is squeezed into a tiny space, it tears a hole in space-time, a black hole. Black holes are the ultimate consequence of warped space-time. They are not just objects, but regions where the universe itself is twisted beyond recognition. This is where our story truly begins. Black holes are born from the deaths of massive stars. Only stars at least 20-30 times the mass of our sun can become black holes. These giants burn fiercely, balancing outward fusion pressure against gravity. When their fuel runs out, gravity wins, collapsing the core in an instant. This collapse triggers a supernova, blasting outer layers into space and seeding the cosmos with heavy elements. If the core is massive enough, it collapses into a singularity, a point of infinite density. This is a stellar mass black hole, the most common type in our galaxy. But there are even bigger monsters, supermassive black holes, millions or billions of times the sun's mass, lurking at galaxy centers. Their origins are still mysterious, but they likely grew by devouring gas, dust, and stars over cosmic time. There may also be intermediate mass and even primordial black holes formed in the early universe. Black holes come in many sizes, but all are born from gravity's ultimate victory. A black hole isn't a thing, but a region where reality breaks down. At its heart lies the singularity, a point of infinite density where physics as we know it fails. Surrounding this is the event horizon, the invisible boundary beyond which nothing escapes. Cross the event horizon and escape is impossible, even for light. The size of the event horizon depends on the black hole's mass. Most black holes spin, creating an ergosphere outside the event horizon where space-time itself is dragged along. Inside the ergosphere, you're forced to move with the black hole's spin. These features, singularity, event horizon, and ergosphere, define the anatomy of a black hole. They mark the edge of what we can know about the universe. While the inside of a black hole is hidden, the area just outside is one of the universe's brightest, most violent places. Matter spirals into a black hole, forming a superheated accretion disk that glows brighter than entire galaxies. Friction in the disk heats gas to millions of degrees, emitting powerful X-rays, one way we detect black holes. Gravity also bends light around black holes, creating gravitational lensing and even Einstein rings. This bending lets us see black holes by their effect on background light. Black holes also warp time. Near the event horizon, time slows dramatically. To a distant observer, someone falling in would appear to freeze at the edge, fading away. For the falling person, time feels normal as they cross the point of no return. These effects, extreme light, warped space, and twisted time, make black holes cosmic laboratories. They reveal the universe at its most extreme. Black holes were once just theory, but we've found them by their effects on nearby stars and matter. At our galaxy's center, stars orbit an invisible mass, Sagittarius A*, with 4 million times the sun's mass. X-ray binaries reveal black holes as unseen companions devouring matter from nearby stars. The first black hole candidate, Cygnus X1, was discovered this way. In 2015, LIGO detected gravitational waves, ripples in space-time, from merging black holes, confirming their existence. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow in galaxy M87. We now see, hear, and measure black holes across the universe. The hunt has become a cosmic reality. Black holes challenge the two great theories of physics, Einstein's relativity and quantum mechanics. Stephen Hawking showed that black holes aren't completely black. They emit faint Hawking radiation due to quantum effects at the event horizon. This means black holes slowly lose mass and can eventually evaporate, though it takes longer than the age of the universe. Hawking's discovery linked gravity, quantum mechanics, and thermodynamics in a revolutionary way. But it also created the black hole information paradox. Does information that falls in disappear forever, violating quantum rules? If black holes evaporate, where does the information go? This puzzle remains one of the biggest mysteries in physics. Black holes force us to confront the limits of our knowledge. They are the crossroads of the very large and the very small. Black holes are now central to astrophysics, testing the limits of our theories. Their gravity lets us probe Einstein's relativity, while their role in galaxy evolution shapes the cosmos. Supermassive black holes launch jets that regulate star formation and sculpt galaxies. The mathematics of black holes even hints at wormholes, tunnels through spacetime, though these remain speculative. New observatories and gravitational wave detectors promise deeper insights and new discoveries. We still don't know how supermassive black holes grow so large, what happens at the singularity, or how the information paradox is resolved. Black holes born from darkness continue to illuminate the universe's greatest mysteries. Our journey into the abyss is just beginning.